now, although we haven't done one with a range. And we've also done it as a part of other problems, specifically our graphing problems. And like I've been saying all semester, I keep alluding to these big bad graphing problems. They're really not that bad. It's all a bunch of stuff that we've learned and gone over plenty of times. Like I mentioned in the breakdown. So this is old algebra. We should be relatively comfortable with finding the old algebra. And, you know, you can probably get away with some of these graphs without finding the intercepts. But at the same time, these are the concrete points that are gonna guide you towards that graph. And, you know, actually, I don't want to say that you could get away with it without putting the intercepts down, because there's a good chance that Dr. Zalecki will be grading for those specifically. When I say that if you skip a step, you won't. So I said earlier that if you don't include all of these steps, you wouldn't necessarily miss out on points. We did an example last week, and I'll reference the examples from last week a couple times here throughout the recitation, where, for example, there wasn't an inflection point. And I mean, if you have to do the work in order to determine that there is no inflection point, then that's a different case. But if you can recognize that there will be no inflection points early on, then there's no point in wasting your time writing out an inflection point. That's what I mean when I say that you're not expected to do every little aspect of of these steps, if that one particular step, if you know that it doesn't apply to the graph. But getting back to this problem, so we're asked to find these extreme values. So we know we got to find the critical point. We find the critical point by setting the derivative equal to 0. So what is the derivative of this function f of x? We're going to find that by doing the power rule. We should be fairly comfortable with our algebraic manipulation at this point, or not, excuse me, our differentiation at this point. Then we factor out a 3. And then finding a factor that'll satisfy such that both are such that when you multiply, you get 8, and when you add, you get -6. So those factors are going to be x minus, or 4 and 2. And so we get our x minus 4 and x minus 2, excuse me. And then we'll get that our critical points exist at 2 and 4. And then in order to determine so there are 2 ways that I have shown you guys how to determine whether or not you're dealing with a max or a min. One of them is to just plug in points to the left and the right, and to see, so if you're dealing with, if you're dealing with, say, the function -x squared, no translation, there's no plus or minus anything, then if you were to look for f of -1 and f of 1, you'd get the same point. So that wouldn't necessarily help you in determining whether or not it's a max or a min. Then maybe you'd have to find f of -2 and f of 2. You need to be able to, so in the same way that when we look for a change in the function, we do y1 minus y2 over x1 minus x2, you need to find a couple of points in order to determine for certain whether or not you had a max or a min. The way that I have taught you guys how to do this on the graphing problems is to use a number line, which we will do later on. But for this problem, we don't necessarily have to, and so we will not use a number line. But if you wanted to, you could absolutely use a number line. And if you're the type of person who likes to keep things consistent, then I would definitely recommend that. So I never unveiled this. The reason why this problem, I wanted to bring it up, why it's a little bit different, we're going to talk a little bit about local and global extrema and how to treat those when we're dealing with a function with specific parameters. So if we're dealing with the function x cubed on -infinity to infinity, so we're not given a specific range, then this would be our local and our global max, and this would be our local and our global min. We wouldn't be able to assert that any part of the function to the left or the right was extreme, because that would tend towards infinity, and you can consider that to be end behavior more so than you would. So we don't call those maxes and mins, is basically what I'm getting at. But when, say I were to tell you that I wanted you to find the maxes and mins, we'll call this A and B, between A and B. Then we've got these endpoints here to concern ourselves with. And this endpoint here is greater than this local max. And so then our definition of what a global max is changes, because we're no longer talking about just what we consider to be a global max or a min. We're talking about the function values within the specific range that we're given, which one has the greatest value. We don't treat it that way when we're tending towards positive infinity or negative infinity, because we can't get a finite max or min in that way. But when we are given a range, sometimes that will change whether or not we label something as a global or a local max. And that's what's going to happen with this problem. So first, we're going to find f of 2 because we found that we know that there's going to be a critical point there, and we get that to be 18. And we'll talk about what that is after we figure out what all the other function values are. And by what that is, I mean whether or not it's a global, local, max, or min. So then f of 4, when we plug that into the function, and today I don't do a lot of explicit algebra. This is going to be probably the one time that you see me plug into a function, whether it's first, second, or third, original function, first derivative, or second derivative. Just FYI, I'll just give you the values. And then also, while I'm thinking of it, so just as a reminder, original function, we should all be comfortable with those. First derivative, so when we set the original function equal to 0, we're finding the intercepts, and we'll do that in this problem. When we set the original or the first derivative equal to 0, we're finding critical points, maxes or mins. And then when we set the second derivative equal to 0, we're finding inflection points. So changes in concavity. And that's something that you should absolutely have memorized. I've gotten a couple emails asking for an explanation on the difference between those. So I thought I'd mention that really quickly. All right, so we found the function values at the critical points. So one of these is probably going to be a max, one of these is probably going to be a min. So since this is a polynomial, there's no possibility for irrationality. So the function, it's not going to look like a sinusoidal curve like this. But when you're dealing with a normal function that doesn't have any sort of interfering aspects that are going to cause it to be funky in some way, you're going to have some sort of a pattern where it's max, min, max, or min, max, min. So you can kind of expect a pattern in that sense. And since this is a normal polynomial, we kind of assume that that's going to be the case here. And so we found our function values for our critical points, and we need to do the same for our endpoints for the reasons that I've just explained. The fact that we are given a range changes the way that we treat this function. And so we're going to look and see what f of 0 is. And so far, this is looking like our global min. And then we look to see what f of 5 is. We get that that is equal to, oops. It is equal to f of 2, which is 18. So before we address the fact that these two are equal, let's talk about these two, or let's just talk about what the min is. That one's going to be easy. So the global min is going to be this endpoint here. So our absolute min. Relative to these other 2 points, this is going to be our relative min, our local min. And these two should sort of make sense. So if we know that this polynomial, it's a cubed function, it's going to be curvy. If we can picture that, if you wanted to do more work and plug in points and be sure, you can always do that. But based off of what we know about how polynomials exist, specifically cubic functions, even though this isn't going to be your typical cubic function because we've got these other interacting aspects of the function, we're going to kind of assume that, okay, we've got a max and we've got a min. We're going to, of these 2 critical points, one's going to be a max, one's going to be a min, because it's not possible to draw 2 minima without somehow having a max in between. And so now we've got to address these values of 18. And this is a little finicky, just because there's not a great explanation for what I'm about to say, but basically this is a local max. And then we're going to call this our global max, our absolute max. And the best explanation I have to offer for you guys, and I don't mean to say that this is something you should memorize, because this should sort of make sense. But if we're regarding this min here as a local min, then similarly we'll regard this one as our local max. And since we know that the function is just going to continue and get larger and larger, and that this f of 5 value is going to be smaller than f of 6 per se, we're going to call this our absolute max. And there's not really a great explanation for that. I almost wanted to teach it differently than the book did, but that didn't seem like a good idea the day before the exam. You guys wouldn't have much time to unlearn what I taught you if I taught it to you incorrectly. So this is the answer that you would find in the back of the book. If I believe odds are in the back of your book, this is the answer that you would find, and that is my best explanation as to why. Does anyone have any questions? Did I not explain that well enough? Okay. Yeah, first recitation was pretty quiet too, which I'm hoping is a good silence. You guys are well studied and well prepared. Okay, so got a decent amount of time to work on the next problem. All right, so these big bad graphing problems that we've been talking about all semester and working on for about half of this unit. So we're going to graph this given function here. Did I hear someone say something? Okay. We're going to be graphing f of x, and off the bat, we notice that we've got some junk in the denominator. So we're probably going to be dealing with some asymptotes, 1 or 2 probably, because we've got 2 factors here. Technically 3, but we would get the same factor from this x minus, we would get the same, we would get the same asymptote from this doubled factor here. We would still get x equal to 3. But we'll deal with that later. One thing that I added in, so my format from last week to this week, it's going to be basically the same. I added in domain because I got some emails about the domain. And I also got some emails about symmetry. Symmetry can be useful. At this point in the game, if you're not comfortable with symmetry, it's just one more thing that I wouldn't add in because it's entirely possible to graph these without finding symmetry. But if you are comfortable, then I would look into it because it can speed up the process and save you some time on the exam. Basically, if you've got an even function, x squared, even referring to its power, that's going to be a symmetrical function. If you've got an odd function, x cubed, that's going to be an odd function. And just for visual representation, the functions will look something like this. So if you know that a function is going to be symmetrical, then you can, I don't want to say that you can do half the work because you're still going to be doing the majority of the calculations. But when it comes to graphing it, you can assume that the right half is going to look like the left. And so if you'd like some more on that, you can shoot me an email tonight, and I'll do my best to get back to you. I do have an exam of my own tomorrow, or you can watch a Khan Academy video on symmetry. But it's one of those things that you're not going to lose out on points for not using it. If you can come up with the correct graph without finding the symmetry, that's totally fine. So I did put up domain though, just because it ties in so easily with finding our asymptotes almost to the point of being redundant. So we've got our domain here is going to, so if we, like when we find our asymptote, our vertical asymptotes, we set the denominator equal to 0, and we'll do that in a few steps here. So we know that if we set this denominator here equal to 0, x is going to be equal to 0 and x minus 3 is going to be equal to 0, and neither of those two things can happen or the function will be irrational. We'll have a 0 in the denominator. And so the domain is all x values except for x equal to 0 and x equal to 3. What we're more used to seeing that written as is function or is interval notation. And so from negative infinity to 0, union with 0 to 3, union with 3 to infinity. That's our domain. Those are the possible x values. Now, like I said, you don't necessarily have to write up the domain, but if you do write up the domain and you write it up incorrectly, then you could possibly lose points. So for example, if you did a closed bracket here, that would represent a conceptual misunderstanding, well, a misunderstanding of what this symbol means, first of all, and a misunderstanding of what it means to have a 0 in the denominator. So be careful with those. But I think that this is something that we've done in plenty of algebra classes in the past, and it has come up at the beginning of the semester. So I wouldn't be too afraid of using your interval notation. So that's domain. Now we're going to move on to finding our intercepts. So we've got our x-intercepts and our y-intercepts to address. If we're going to, so we've got two options then, set y equal to 0 or set x equal to 0. When we plug in x equal to 0, we get something irrational. So then there is no x-intercept. When we plug in y equal to, or when we set the function equal to 0, when we set y equal to 0, if you remember from, I believe it was question 9 in last week's recitation, we had another situation where we had a fraction that we were trying to set equal to 0 in order to find either the critical point or the inflection point. But when the numerator has no x value, it's not possible to set that fraction equal to 0. When we're trying to find irrationalities, we set the denominator equal to 0. When we're trying to find intercepts, we set the I shouldn't just say intercepts. When we are trying to find the intercepts, we set the original function equal to 0. When we're trying to find critical points, we set the numerator of the first derivative equal to 0. And when we're trying to find inflection points, we set the numerator of the second derivative equal to 0, if you're dealing with a fraction. So numerator is for finding rational values that actually exist that we're looking for, that we're going to use. Not that we won't use what we find by setting the denominator of the function equal to 0, but that is my point that I'm trying to make. So the point being that you can't set this equal to 0 and that there are no intercepts because we've got this constant in the numerator, and in order to find when a function or when a fraction is equal to 0, you've got to set the numerator equal to 0. And so it's not possible. We've got no intercepts. Next, we'll move on to asymptotes, starting with horizontal asymptotes. So if you guys remember, this is, we're going to evaluate this using limits. This is end behavior. And I evaluated this all as one because we get the same answer regardless. There's really one concept behind this. From last week when we did horizontal asymptote evaluations, we did it as two separate ones, and we talked about the concept of larger and smaller infinities. I would definitely brush up on that in last week's recitation recording if you aren't as familiar with that, because I could definitely see that being part of a problem on this exam. But as far as this goes, doesn't matter if you're dividing one into infinity groups or negative infinity groups. You're dividing it up into such small pieces that it's going to be 0, and 0 has no sign. So it doesn't matter. I shouldn't say it doesn't matter, but that's why I put them together as one. If you plug in positive infinity, you're going to get positive infinity times infinity minus 3, which is going to be infinity squared. 1 divided by infinity squared is always going to be equal to 0. If we did the same with negative, it wouldn't make a difference. It would be infinity cubed, I misspoke, but it wouldn't make a difference because we'd end up with negative infinity, and 1 divided by negative infinity is still just 0 because 0 carries no sign. And these are our horizontal asymptotes. Or our horizontal asymptote, our end behavior is going to be such that our function is going to, whether it's on top or bottom, I don't know yet, or we don't know yet, but it's going to be along the x-axis. Our end behavior, we're going to tend towards probably positive and negative infinity along the x-axis. Any questions on evaluating these limit statements? You can also expect to have a limit problem or two on your exam in more of an isolated style, like with this problem. So we find our extreme values in order to figure out what the graph is done in this problem. But you'll have one or two problems that are specifically find the absolute and local extreme values, specifically evaluate this limit, not just a part of the bigger function. Or of the bigger graphing problems, excuse me. All right, so now we've got to find our vertical asymptotes. To do that, we're going to set our denominator equal to 0. There's another way that you can do it, but we'll talk about that in a second. Setting the denominator equal to 0, we get that x is either equal to 0 or x is equal to 3. And these are our vertical asymptotes. And these are going to be really helpful in guiding us. And we're going to use them. We're going to use our vertical asymptotes when we talk about concavity as well, similar to how we did last week. Excuse me. So another way that you can evaluate these is, again, using limit statements. So you could look to see what the limit as x tends to 0 and the limit as x tends to 3 is. When I say another way to evaluate, I guess I kind of got ahead of myself here. So if we're just going to talk about x equal to 3. This is not the graph for this problem. We're just talking about specifically we're just focusing on this one for a second. So we've got x equal to 3. At this point, we don't know if it's to the left or to the right, but we have two options. It could tend toward positive infinity or negative infinity. So what I've often found is that students tend to shy away from evaluating limits in their own problems. If they have the option not to, which you do, you can get around this by plugging in values and seeing if your value is, say, for example, I want to see where 2.5 is. If 2.5 is above the x-axis, odds are you're tending towards positive infinity. So let's look and see what 2.75 is. Is it increasing? Then you're tending towards positive infinity. You don't have to evaluate these using limits, but I did want to throw that up there in case you saw it in the book or in a video online. It's the same sort of deal as before, how I mentioned. Well, I mean, you can plug in points to work around a lot of this stuff, but the basics that you're going to have to stick to. So plugging in points is going to be your best friend. X-intercepts, obviously, that's part of that. You're definitely going to have to look for your critical points. If there are no critical points, you're definitely going to have to look and see if the function is increasing or decreasing and on what intervals. same sort of deal. You're definitely going to want to look for your inflection points, but if there are none, you're still going to want to look for concavity. And then unless it's a simple polynomial, you're probably always going to want to look for your asymptotes and end behavior as well. So now we're going to move into the new calculus. So far we've done algebra, and then so we've done asymptotes already, but this is old calculus, first unit calculus, what we did at the very beginning of this course. And now we're getting into our more recent calculus, finding critical points and inflection points, and then the intervals of increase and decrease and concavity. So we're going to set the first derivative, or we're going to find the first derivative, excuse me. So you might notice that all of a sudden we've got this x in the numerator. Earlier, I made a big fuss about how there was nothing in the numerator, and so we couldn't set it equal to 0. Just wanted to point out that technically this is still in the denominator. I've just done a fractional power manipulation because I wanted to do this problem using the quotient rule. I thought that it would save me time rather than having a long string of positive and negative powers and having to manipulate those. I thought it would be easier to do one fractional power manipulation and then do the quotient rule. But again, you can use any of these differentiation techniques as long as they apply and you apply them correctly. You could use a combination of the power rule, quotient rule, or product rule, and you'll still get the same answer. It doesn't matter what method you use, as long as you manipulate it correctly ahead of time. And so when we do the quotient rule, this is what we get, disregarding my little, not disregarding my orange doodles, but we've got the derivative of the first times the second minus the first times the derivative of the second over the second squared with a manipulation. And then we get this factor x minus 3 in the numerator and in the denominator. So if this factor x minus 3, if it didn't appear next to this 2x, we would not be able to divide by x minus 3. I've seen some mistakes like this on the homework, on some homeworks, where students will divide a factor out of maybe just the left term and neglect the fact that there is no factor to divide out of the right term in the numerator, and that is incorrect, and you will absolutely lose points for that. So what I'm saying is make sure that if you're going to be canceling something out of a denominator, that you've got something to cancel for all aspects if it's additive or subtractive of the numerator. And once we do that, we get negative x plus 3 minus 2x. And then the denominator is the same, except we now have this to the third power. And when we simplify this here, we get 3 times 1 minus x. Well, you could just do 3x minus 3, or 3 minus 3x, and simplify it the same way that I'm going to by setting 1 minus x equal to 0. You could set 3 minus 3x equal to 0 and get the same answer, no problem. And then we get that x equal to 1 is a critical point. And just like with this problem up here, we now have to qualify what that critical point is specifically. So we draw up our number line. It's possible to get around drawing up the number line, but specifically with these problems, I would definitely not recommend that. There's so much information swirling around in your brain, and you have no idea what this graph is going to look like until you get towards the end and you power your way through. So this is exactly the type of visual that you want to have. In the past, when I've taught these problems, I didn't do that just because I recognized that it wasn't necessarily something that you guys could apply on your own in an exam. But what I would do is I would write up the number lines, and then I would bring it back down to the graph, and I would copy and paste the number lines so that the x-axes would all line up and we could all visualize where the changes in concavity and increase and decrease happened. Because if you're going from symbols to a graph, you've got to have some connection between the numbers and the visual. And so these number lines are going to be pretty important. What I'm saying is you should probably use them, even though there is a workaround. So we have got one critical point. That doesn't necessarily mean that all x, or that the whole function to the left of x equals 1 is going to be increasing or decreasing, and that the whole function to the right of x equals 1 is going to be the opposite of that. We know from our problem last week, again, I think I'm referencing problem 9, that our vertical asymptotes are also candidates for changes in inflection. And when I say a change in inflection, or changes in, I'm getting ahead of myself, are also candidates for a change in the first derivative. So we're going to take a look at that as well. And the reason why we know that is, say if we look back at this graph from last week, since they're basically existing in different parts of the graph, we have no idea what they're going to be other than what the asymptotes guide us to, or how the asymptotes guide us. And so it's entirely possible that both of these could be decreasing, both could be increasing. And so it's always important. I would go overkill on this. Every single pertinent piece of information that you think you have. So you've got a critical point, you've got your vertical asymptotes. You're not quite sure if the vertical asymptotes are going to have a bearing on whether or not the function's increasing or decreasing, on whether or not the function's concave up or concave down. Overkill would be the way to go with this because, like I said, there's a lot going on in your head. You don't necessarily have the foresight to know what this graph is going to look like. So just assume that there's probably more to it than you know. And then that way, when you plug in those values, maybe you've done like 1 or 2 steps of extra work, but then you're not going to miss out on points because you've assumed something incorrect about the graph. And I'll explain this a little bit more when we get to inflection points, when we get to the second derivative test, and it'll make a little bit more sense when I'm getting at later. But we're still going to use all of the same boundaries. We're going to use where we know our vertical asymptotes are going to be, and we're going to use our critical point. And we're going to plug in values to the left and right in order to figure out what the derivative is, what the sign of the derivative is. So like I said, I'm not doing a whole lot of explicit algebra today, but f prime is going to be less than 0. F prime of -1 is going to be less than 0. So that means that to the right of 0, f of x is decreasing. It's very important to keep that in mind as you're going through these. Then f of 1/2. So between 0 and 1, f prime of x is still decreasing. So if we talk back to, so I mentioned a sinusoidal curve. Normal functions, we expect to go from increase, decrease, increase, or excuse me, from max to min. I guess you could still say increase, decrease, increase, decrease. But when we throw in possibilities for irrationality, like we have with this complicated denominator that we have, these aspects of the function aren't going to exist necessarily within the same pattern that we're used to seeing them. And so that's why I say that overkill is better, because you can't, if you don't know what this graph looks like, you don't know what kind of curveballs it's going to throw at you. I don't know. And I've been doing these problems for, I don't know, I started doing them in junior year of high school, and I still will do these problems with the overkill mentality. And then when you get to the end of your problem, boiling down what all of your information into your little puzzle pieces to keep things from being overwhelming. But at the same time, if you don't know what this function is going to look, what this graph is going to look like, then don't assume that you know that this function is going to change from negative to positive. Because I've seen people make mistakes on exams in the past where when they're like, okay, it's negative and I'm used to seeing the next one be positive, so I'm going to assume that this one's positive and then this one's negative and then this one's positive. And then their whole graph is thrown off. So overkill, name of the game. We get positive for f prime of 2, and we get negative for f prime of 4. And so the one point that we want to classify here, because this here isn't a maximum just because it's changed from positive to negative. There is no function value at x is equal to 3. The only max or min, the only candidate for an extreme point that we have is x equal to 1. And we go from decreasing to increasing. And so we know we've got a min, our only min. And for the sake of time, I just threw up what that function value would be, because that's where this is definitely, you definitely want to find the function values of your maxes and mins and of your inflection points if you have them, because again, those are going to be your concrete points that guide you. Those, your intercepts x and y, and then your asymptotes are going to be your most helpful information. The first things that you should draw down or write down, and then it's filling in the blanks from there. So now we'll move on to the second derivative. So f double prime of x taken by the quotient rule. Again, at this point, I would hope that everybody's comfortable with the quotient rule. And then if we're looking, so again, if we're finding an inflection point, we're setting the numerator of the second derivative equal to 0. 6 can never be equal to 0, so that's negligible. So let's just think about this right here. If you were to plug in -1, if you were to plug in 0, if you were to plug in 1, if just plug it in your head really quickly, you'll see that no matter what you plug in, negative or positive values, you're always going to get a positive numerator. And so then we can say that for all x values, there are no inflection points. If the numerator is always going to be positive, then at no point is it going to be equal to 0, and there is no x value that corresponds to an inflection point. That being said, just because there isn't an inflection point doesn't mean that we aren't still interested in what the concavity is, and to the left and right of other boundaries that we know to already exist. And that's going to be the case. You should always, so if you don't have an inflection point, you should still be trying to find out what the concavity is, because concavity, after you've put down your puzzle pieces, concavity, your ranges, your number lines for first and second derivative, so whether or not the function is increasing or decreasing, and whether or not the function is concave up or concave down, that's sort of like phase 2. So you draw your concrete points, that's what's gonna, and then from in between your concrete points, whether or not the function is increasing or decreasing or concave up and concave down, that's gonna guide you to sort of fill in the blanks, as I keep saying. So you always want to assess your concavity. Concavity is specifically helpful. So I didn't do as much of a detailed one as I did with the first derivative, but it's the same process. To the left of 0, we get that it's concave down. In between 0 and 1, we get concave up. In between 1 and 3, we get concave up again. So this is another example of how you don't want to assume that it's going to follow some sort of a pattern. And that should make sense specifically because we're talking about functions that have vertical asymptotes. And so since we're dealing with these irrationalities, the function is probably going to behave not in the same rational way that we're used to seeing. And then again, we get that the function is increasing at this point. Or I keep saying increasing, that it's concave up, excuse me. All right, so we've got all of our important information, but there's a lot of it. We've written a lot of math down for one problem. And so, like I said, overkill is going to be very helpful in terms of making sure that you don't miss important information. But once you've done all this math, you've got to find some way to navigate the chaos and to boil things down to what's actually pertinent from all this information that you've just found. So personally, I would not be concerning myself with the domain at this point. There are no intercepts, so I don't have to write anything down about that. End behavior, I know that my function is going to be kissing up against the x-axis, so that's important to know. Vertical asymptotes, we've talked pretty extensively about those. We've got, there they are. And then x equals to 1 is a local minimum. And finally, no inflection points. So we're not going to circle the entire number line, but you should definitely be referencing the f prime number line and the f double prime number line. But this is the stuff that I've circled. This is the stuff that you're going to write down first. So the phase 1, as I've called it. So we're going to have an asymptote at x is equal to 3. We've also got an asymptote at x is equal to 0. And we've got another asymptote at y is equal to 0. We have no intercepts, so we don't have to worry about that. At x is equal to 1, we know that the function value is 1/4 and that this is our min. So since we know that, we're probably, based off of where the asymptotes are here, it looks like it's going to be, it looks like it'll have no other choice other than to be concave up. And if we look at, in order for it not to cross these asymptotes, because there's no way it can come down here, there's no way it can come across and be concave down in any other way. And so we can sort of assume before we even look at our second derivative number line that it's going to look something like this. And then if we do look at our number line, we get that it's concave up between 1 and 3, between 0 and 3. So let's take a look and make sure if we expect the function to look like this, so that's supposed to be our min. If we expect that the function should look something like this, then let's go take a look and make sure that we go from decreasing to increasing on the first derivative. And look at that. At the min, we change from negative to positive. So we're just fact checking ourselves here. I want to point out, so if you were to look at this answer in the book, it would not look like this. So it would look something like that, I believe. But with something as obscure, I don't know if that's necessarily the right word, with something as so if you're not the best artist, no big deal. Just label, say that this is the min. F of 1 is your minimum if you're not sure. When I show the other graph, I'll show you what I mean, the difference between like what the graph is supposed to look like and how I drew it for this graph. I'll come back to that in a second, but you're not going to get penalized for not being a good artist if you correctly represent all of the calculus and like by labeling it or something like that. We're not going to be upset with you if your curve doesn't look the right way. So now we have got the left of this asymptote to deal with and the right of this asymptote to deal with. So from last week's, I don't know if you guys remember problem 9, we had, well, I might as well pull it up. So we've got the left of this asymptote to deal with and the right of this asymptote to deal with. If we are graphing a quote unquote function, there is no possible way for there to be another aspect below this horizontal asymptote because then it'll violate the horizontal line test and we no longer have a function. So that's something that that knowledge we can use to our advantage because we know that, okay, if the function exists down here, then it cannot exist up here. So between these two, let's take a look at specifically concavity. Concavity is going to be really helpful to figure out whether or not you're above a horizontal asymptote or below. And we're going to use that in conjunction with our first derivative. If to the right of 3, it's concave up, it's probably not going to look like this because then it would be crossing asymptotes. So from that alone, we can pretty much figure out that the function is going to look like this. These asymptotes are meant to guide you. And we know that the function is going to be concave up to the right of x equals 3. So let's just double check and make sure that the function goes, or that corresponds with what we know about the first derivative. And look at that. We know the first derivative to be decreasing to the right of x equals 3. So we're on track. Now let's take a look at the aspect of the function that is to the left of x equals 0. Again, we know the function to be decreasing, or to be, so we know the function to be concave down because the second derivative is negative. So the function is probably going to be increasing. Oh, no, it's not. Concave down and decreasing. Oh, that makes sense. So I believe at this point, I might as well just reveal the graph. Then it's going to look like this. So going from left to right, we see that the function is still decreasing and it's concave down. By the same sort of logic that we used here, I usually start with concavity because so if you picture it as, I don't know, a cup or as a parabola, whatever it is, you can sort of picture the function kind of fitting between your arms in a way. I don't know, that's how I visualize it. And then I'll go and I'll check with the first derivative and make sure that I'm on the right track. And so the difference between what I mentioned earlier, so this curve here in the function, if you look in the book, it kind of comes straight down and then it curves out like that. And this would still be an acceptable answer. I would just maybe label this your min to make it clear because technically there's a point that's lower than this one on the way that you've drawn the curve. But if you point out to the grader most likely being Dr. Zalecki because he grades the free response part of the exam. If you point out to the grader, hey, I recognize I'm not the greatest artist, but I do know the math. I know that this is supposed to be a minimum and I'm labeling that for you. You will get full credit for it. Okay, so we've got about 5-6 minutes for questions. First, are there any questions on the graphing problem? Okay. Again, I'm hoping that is a confident and well-studied silence.
Could you go through like the steps again?
This?
Yeah.
Yeah. All right. So for today's problem, I did the horizontal and vertical asymptotes earlier. And honestly, I would recommend, if you are someone who likes to memorize, that you pop this one up to number 2 and do it second. The reason for that being is that sometimes when there are sometimes we're going to use those asymptotes to guide us for our first and second derivatives. So we should probably do those before we do our first and second derivative number lines. So if we're thinking, and then it becomes easy to think of in terms of, all right, we're going to start with algebra, the oldest stuff that we know. We're going to find our x and our y intercepts as concrete points to guide us. Then we're going to go to first semester calculus or first unit calculus. We're going to find end behavior and vertical asymptotes, which all in all is like finding vertical asymptotes is very easy. And if you're comfortable with your limit evaluations, finding your horizontal asymptotes, your end behavior isn't all that tough either. So we've got old algebra, old calculus. Then we get into new calculus. And you can think of new calculus in two groups. You got first derivative calculus and second derivative calculus of what we taught you so far. So for the first derivative, find your critical points and then find your intervals of increase and decrease. So that kind of all wraps in with your maxes and mins. If you go from increasing to decreasing, then you've got a max. So finding your intervals of increase and decrease as it pertains to your maxes and mins or your asymptotes, if any, that is your first derivative calculus. Then you do the exact same thing with the second derivative. And so you'll find those points of inflection, if any, where the second derivative is equal to 0. And then using those points of inflection as boundaries in conjunction with your asymptotes, if any, you'll then figure out the intervals of concavity, whether it's concave up or concave down. So algebra, first unit calculus, first derivative calculus, second derivative calculus. That's kind of the four groups that you can think of it as.
I have a question about the max and mins.
Okay.
So do we have to list them as like an ordered pair or like just the value that they are? Like, are we supposed to plug them back in and then like put them into an ordered pair and then like label that as like the max and the min, or?
This is totally fine, this format here. You can also do it as an ordered pair. If you mean like in parentheses.